In the first question, we have hydrogen peroxide decomposes to form water and also oxygen. And from the experiment, we're going to collect oxygen on a measuring cylinder, and using the volume of oxygen produced, we're going to calculate the molarity of the hydrogen peroxide. So let's go through into the procedure real quick in lab. Right, so from the experiment that we have found that the volume of oxygen produced 180 cm cubed. So we're going to go into writing the result now. Let's get into the calculation. The first one, use the information on page 2 to calculate the volume strength. It says that here 1 cm cube of 100 volume of hydrogen peroxide will produce 100 cm cube of oxygen. So since we are producing 180 cm cube of oxygen, so we can divide that with the volume of hydrogen peroxide that we use to get the volume strength of Fa1. Next one, calculate the number of mole of oxygen collected. So we can divide the volume of oxygen with the molar volume here. We have 180 cm cube of oxygen produced divided by 24, but since this is in dm cube, so we need to convert into cm cube as well. So we have 7.50 power of negative 3 mole. So use your answer to 2 to calculate the number of mole of hydrogen peroxide in the volume of Fa1 added to flask X. The balance equation, we can see that the ratio of oxygen to hydrogen peroxide is 1 to 2. Hence, the mole of hydrogen peroxide must be the mole of oxygen multiplied with 2. So we have 7.5 power of negative 3 times by 2, we have 0.0150 mole. And calculate the concentration of hydrogen peroxide. So we have mole divided with the volume that we use, and we can have the molarity. So we have 0.0150 mole divided by the volume 150 cm cube. However, we need to convert this into dm cube, so divide by 1000. We have 0.100 mole per dm cube. Make sure all of the answers given are at least 3 significant figures, because we need to have this one, 1 mark for this. Next question, a source of error in this experiment is that some oxygen escaped before the bung can be inserted. So suggest a change to the practical procedure given in A to reduce the source of error. As you can see here in this procedure, so we need to tip Fa2 into the flask, and then we need to replace the bung immediately. But what we can do is to improve this. We can put Fa2 inside here, floating in a weighing boot, so that it will not react yet. And then just set up the apparatus as such. And when we're ready, we can just shake the flask to make the Fa2 react with Fa1. So since this system is done in a closed system, so as soon as oxygen is produced from the reaction, it can straight away be trapped in the measuring cylinder. For this question, you can draw if you wanted to. So the error in reading of 50 cm3 measuring cylinder is plus minus 0.5 cm3. Calculate the maximum percentage error in the volume of hydrogen peroxide. So we have error, percentage error is equivalent to the probability 0.5 cm3 divided by the total volume 50 cm3 and multiply with 100 because this is in percentage. So we have 1.0%. And the volume that we have taken for this experiment is 150 cm3. That means we use the 50 cm3 measuring cylinder 3 times. So for the percentage error, we need to multiply with 3 as well. So 1.0% multiply with 3 times, we have 3%. So explain why the presence of 20 cm3 of air in 250 measuring cylinder before the start of the experiment will decrease the accuracy of the result obtained in A. So since we have the volume reading caused by air, which is the thing that we don't want, we just want the volume produced by the oxygen. So we will need 2 readings to find the volume of gas evolved. And more reading that you've taken, you will have a higher error. So that means you will have twice the percentage error of taking the volume. If you repeated the method described using half the mass of Fa2, what volume of gas would you expect to collect? Explain your answer. So our Fa2 is only a catalyst. Catalyst will speed up the reaction, but catalyst will not alter how many of your product will be produced. So regardless of using half the mass of FO2, there will be no change because the FO2 is only a catalyst. So let's go ahead into question 2. So in this question, we need to identify the concentration of hydrogen peroxide that we use in experiment 1, but this time we're going to use a different method or a different approach, which is a titration with potassium manganate with a dilute sulfuric acid. So let's go into the experiment real quick in the lab. So let's get straight into answering the question. So since we have done the titration, so we can draw the table for the result for rough and also accurate titration. So in the table, make sure you have the final burette reading, the initial burette reading, and also the volume of Fa3 used. And all of the volume must be 2 decimal places because that's the accuracy of the burette. Hence, using the accurate titration, we can determine the volume of Fa3 used in the titration. So that will be plus both of the accurate titration and divide by 2. So we have 33.00 cm cubed. Calculate the mole of manganate ion present in the volume of Fa3 calculated. So we know that the molarity of Fa3 is 0.03. So we can multiply that with accurate titration to have the mole. However, the volume used is in cm cube, so we need to convert into dm cube. Next, we need to calculate the mole of hydrogen peroxide. So the ratio between the manganate ion and also hydrogen peroxide is 2 to 5. Hence, the mole of hydrogen peroxide will be 9.1 multiply 10 to the power of negative 4 times with 5 divided by 2. Then we need to calculate the concentration, so mole divided by volume, we can get the concentration. Divided by the volume of hydrogen peroxide used, which is 25 cm cube. And definitely we need to convert into dm cube, so divide by 1000. 0.0992 mole per dm cube. Alright, so let's move on into question 3. So in this qualitative analysis, we have 3 unknown labeled as FA5, FA6, FA7, and we're going to test this unknown with aqueous sodium hydroxide and then with aluminium foil, and then the next test we're going to identify using aqueous potassium manganate, and then we're going to test with hydrogen peroxide, and then the next one with dilute hydrochloric acid with an addition of barium chloride or barium nitrate. So let's quickly go into the lab. Alright, these are the results. And from the result, we're going to identify the cations and also the anions inside all unknowns. So let's go into Fa6 first. So in Fa6, when we react with sodium hydroxide, it will produce a green precipitate, and where it warms gently, it will turn red litmus paper into blue, which indicate the formation of ammonia. And when we add with an oxidizing agent, it will oxidize. This is because the purple color of the oxidizing agent decolorize. So from the cations table, we can see that when we react with sodium hydroxide, the cations that will produce a green precipitate will be Fe2+. And when heated with sodium hydroxide, it will produce ammonia. That means it also contains ammonium ions. And to identify the presence of anion, we test with hydrogen peroxide, where it relights the glowing spleen, which indicate the formation of oxygen. There is no reaction with hydrochloric acid. However, when we add with Ba2+, it will produce a white precipitate which is insoluble in excess. So from the anion table, it can be known that it contains sulfate ion because it produces a white precipitate, and the precipitate is insoluble in excess of acid. The next one we have is Fa7. So in Fa7, when we add with sodium hydroxide, it produces no reaction even if it's warm. However, when we add aluminium foil, it shows an effervescence and it turns a red litmus paper blue, which indicate the formation of ammonia. So this is actually a test used to identify the anion. So from the anion table, we can see that it's either nitrate or nitrite that will produce ammonia upon heating with sodium hydroxide in the presence of aluminium foil. So to further test this anion, we react with hydrochloric acid, which produces a brown gas. So this test confirms actually the production of nitrite ion because you can see a pale brown nitrogen dioxide when react with hydrochloric acid. However, for cation, we have not much idea about the cation. It only shows the purple color decolorize, which indicate that it undergo oxidation. But there is no further test to confirm the cation, hence the cation is an unknown. It could be a group 1 metal. So let's get into Fa5. So with Fa5, it shows no reaction with sodium hydroxide. Only when it warms gently, it will turn into yellow or brown on standing. And when we add aluminium foil, it shows an effervescence. It also shows no reaction with acidified potassium manganate. Only upon heating the purple color decolorize. And there is no test done for the presence of anion. Hence, from here we can say that there is no evidence on the presence of cation and also the presence of anion. So both are unknown. The next one, describe another test you will carry out to confirm the identity of cation. In order for us to identify cation, we should react with sodium hydroxide, which we have done in the experiment, and also with ammonia. So another test to confirm the identity of cation is definitely reacting with ammonia. So add ammonia. So for Fe2+, which we have confirmed in Fa6, in react with ammonia, it will produce a green precipitate, which is insoluble in excess, and it will turn brown on standing. The next one, write an ionic equation for the reaction that will occur in 2, include state symbol. So this is a reaction that will produce iron 2 hydroxide, which is a green solid. Thank you everyone for tuning in, and whether your school take an exemption or not for the practical 3, I wish you all good luck for your external exam.